Hi, geometry students. Miss Soli here with another lesson that we will put in our notebooks. Go ahead and open to your table of contents. This is 1.4, inductive reasoning. Now, a big part of geometry is logic and reasoning. So this week in geometry, honestly, it's going to feel a little bit like an English class. So stick with me for a little bit of logic work. 1.4, inductive reasoning. So, for example, inductive reasoning, we're just going to start with two examples and then define it after that. Let's see. All right. So I'm going to draw 3 circles. I cut 1 in half. Another circle, I put this into 4 pieces. I'm going to color in this side. And then this circle I cut into 6 pieces. And inductive reasoning, I want you to take a moment and think about what is going to go in the next circle. Notice the pattern you're seeing. Does this tell you enough to know what's going to go here? So this was cut into 2 pieces, cut into 4 pieces, cut into 6 pieces. So this one is going to be cut into 8 pieces. Does the pattern tell you which one is going to be colored in? Which piece is going to be colored in? Because it looks like it's on the top half of the circle each time. And it's like the leftmost piece. So it's going to be this one. We used inductive reasoning based on that pattern to see what comes next. Another example could be like with numbers. Let's say I had 3, -9, 27. What's going to come next? So there's a couple of patterns going on here. Looks like in order to get to 9, I can either add 6, but it's -9. So I can subtract 12 or multiply by 3 to get 9, multiply by -3 to get -9. And 9 times 3 is 27. So it looks like I'm timesing by -3, times by -3. So in this pattern, in order to find out what comes next, we had to figure out the pattern and then do that pattern to find my next term. I could even find the next term, multiply by -3 again, okay? So inductive reasoning is when you find a pattern to predict what will come next. Okay. And when you find your pattern, so like with this one, we found every time it's going to have like 2 more pieces of the pie, or you added 1 more line to cut open the pie, however you want to say that. And the top left pie piece was colored in. So when I'm saying that, when I'm like defining the pattern that I'm seeing, I'm making a conjecture. A conjecture is just an unproven statement, but it's based on my observations. I've observed what has happened, so I'm going to predict what's going to come next based on that. So this is called a conjecture. A conjecture is an unproven statement based on observations. Okay. So, for example, if I had, we're going to do one more pattern of like a growing shapes. All right. And this one, draw this with me pretty carefully. So we're going to draw the first, second, and third like block on this pattern. And I'm going to have you guys draw the fourth. So take a look. Here's my pattern. I'm going to draw one block and shade it in, one square and shade it in. Here's my second. Okay. And my third pattern. Okay. Based on this pattern, can you draw what comes next? Pause the video, try to do it, and then check it with me. All right. Welcome back. What comes next? I'm going to have my shaded piece. Each time it was increasing the number of like squares to the side. So this is the fourth term. This had 2 blocks to the side. This one's going to have 3. 1, 2, 3. 1, 2, 3. So now when you're looking at these patterns, I want to say my question is, how many blocks or how many squares will the next pattern have? And then like generalize it. So how many squares will the 8th pattern have? Will the 10th pattern have? Will the 100th pattern have? Let's generalize it. So let's kind of count up how many squares we've got. Here we have 1 square, 1, 2, 3, 4 squares. 1, 2, 3, 4, 5, 6, 7 squares, 9, 10 squares. So how much is this increasing by each time? Looks like it's 1 plus 3. It added 3, 1 square to each of these 3 sides. And then it added another 3. And then it added another 3. So with this, I want to make a conjecture or an unproven statement based on observations, or sometimes a rule. Okay, so a conjecture here could be something like, we're going to start with 1 block and add 3 each time. Something like that. And then that can you can induce what the next one is after that. Sometimes they're going to have you come up with a rule for this. Rule. And a rule is just like a formula, like a formula. So notice that each time I had a new term on this diagram, I added 3. So if I were to take 3 times, we use the letter N for like, that's the number of terms. So term number 1, N is 1. Term number 2, N is 2. Term number 3, N is 3. Now, if I look at this really carefully though, real quick, 1 times 3 is 3. There's not 3 blocks here. 3 times 2 is 6. It's 2 above 4. 3 times 3 is 9. It's off by 2. 3 times 4 is 12. It's off by 2. So I'm just going to go ahead and subtract 2. This number comes from like how many blocks are in the 0th term, which would be -2. If I take away 3, take away 3, take away 3, take away 3. Okay. Now, the other part of inductive reasoning. So if you make a conjecture. I'm like, it is true that Miss Soli wears a green shirt every day. Based on what I've seen, that's the truth, right? A counter example is going to be a time when you've proven that conjecture wrong, because a conjecture is an unproven statement. It's just based on what I've seen, based on the evidence. I've never seen her wear a red shirt before. So based on what I've seen, she wears green shirts all the time. Counter example would be a picture of me wearing a different colored shirt, which does exist. So a counter example is just one example that proves a conjecture wrong. Like Miss Soli always wears green shirts. Wrong. She can wear red too. Another example could be like the sum of two numbers is always positive. So like sum, I'm adding things together. It's always going to get bigger, right? Well, a counter example, what if I had -2 plus -3? Is this going to give me a positive answer? No. The answer is -5. So it was false. It was a false conjecture. And there's my counter example right there. Another example could be like all Minnesotans say "ope." Is that true? Does every single one of us Minnesotans say the word "ope"? Probably not. Probably not. For example, my brother does not say that. So, for example, a counter example of that would be one person that doesn't. In my case, my brother. So, uh-oh. So that is false. It's more of a stereotype. And I can prove it with a counterexample or disprove it with a counterexample.